So this is a walkthrough video for the GCSE Chemistry Unit 1 higher tier paper for 2021. Now there was no actual exam this year, but this is the paper that was put out. Okay, on to question 1. State the approximate size of the radius of an atom. Well, you can give two possible answers for this. You can either say that it's 0.1 nanometers or 1 times 10 to the minus 10 meters. B, we're told that this table contains atoms and ions. That's important. And then part 1, which one, A, B, C or D, is an ion with a charge of 3 minus. Now, ions have an unequal number of protons and electrons, so that's what we're looking for. So I can see that A is an ion, C is an ion. So now what we've got to do is look for one that has a charge of 3 minus. So there are going to be 3 more electrons than protons. Well, you can see it has to be C, because there are 7 protons and 10 electrons. Which one is found in period 4? Now for this we're looking for atoms. So if I just get rid of these ones, the atoms will have equal numbers of protons and electrons. So it's either B or D. And then in period 4 it's going to be B, because it has 4 numbers in the electronic configuration, and that's how you work that out. So if you look at D, for example, it only has 1 number. That means it only has 1 shell of electrons, so it is in period 1. Identify A. Well, A has 11 protons. That identifies the element. Sodium has an atomic number of 11. Now, it's not a sodium atom because it has 10 electrons. This is an ion. Because it has 1 extra proton compared to the electron, it's going to be Na+. Or you could write it out as a sodium ion, but don't do Na ion. See part 1. The neutron was the last of the subatomic particles to be discovered. Suggest a reason. Well, it has no charge. And the scientist who discovered the neutron was Chadwick. You don't need to put in James there. Chadwick is fine. Next question. The name of the element with a melting point of minus 200 degrees C. Okay, well, if we go to 200 degrees C, we go across, we can see this element has an atomic number of 18. Go to the periodic table, and you will see it is argon. Part 2. Explain in terms of bonding and structure why chlorine has a low melting point. So chlorine is Cl2, and it is a simple covalent or a molecular covalent molecule. And that means that it has strong covalent bonds between the molecules. So if I draw that here, so this bond is strong. However, simple covalent molecules have weak van der Waals forces between the molecules, and they take little energy to break. So it's those weak bonds, those weak van der Waals forces, are what result in chlorine having a low melting point, and that same answer applies to all simple covalent molecules. Explain why aluminium conducts electricity. This is the next question, and this answer applies to all metals. So the question could have asked you to explain why magnesium conducts electricity, explain why copper conducts electricity. Metals have delocalized electrons which can move and carry charge. And put in delocalized because it's not the inner shell electrons that move, it's the outer shell ones, the delocalized ones that move and carry the charge. Part E, formula for silicon tetrachloride. Well, there's 1 silicon and there are 4 chlorines. The type of bonding, well, you can see here, for example, that's a shared pair of electrons. So the bonding is going to be covalent. Question 2. What is meant by the term element? That's just a substance that it's made up of only one type of atom. Don't say that it's a substance made up of only one atom, it's just one type of atom. You could say that it cannot be broken down into anything simpler by chemical means. B part 1. To which group of the periodic table does metal X belong? Well, metal X has 2 electrons in the outer shell. That means it's going to be in group 2 because group number equals the number of electrons in the outer shell. The formula for the metal chloride, well, the metal is X and it's a metal chloride. X will have a valency of 2. So if we swap the valencies over, and the 2 goes after the chlorine, and chlorine has a valency of 1, which we don't put in. So it's just XCl2. And then part 3, a half equation, so that means there's going to be E minus somewhere, to show the formation of chloride ions. So the arrow, the formation of chloride ions. And they are formed from a chlorine molecule, so the Cl2 goes on the left. I'm going to balance it next. We've got 2 chlorines on the left. We need 2 chlorides, 2 Cls on the right. You should also be able to see that on the left this is neutral. Over here this is minus, and there are 2 chloride ions, so that means it's a total of 2 negative, 2 minus over here. The chlorine molecule gains 2 electrons, and then that forms 2 chloride ions. So that's the half equation. In part C then, we'll have to compare the physical and chemical properties of alkali metals and the transition metals. And again, the bullet points are telling us what we have to do. So we have to include density, melting point, colour of the compounds, not the metals. And then the chemical properties to do with the reactivity, reaction with water, and the charges. And this is a comparison, so you need to say what happens to each one. Okay, so here are some of the answers which you could give. So there are the first 3 bullet points, and that covers that first bullet point. Up here, the density, melting point, and the colour of the compounds. As I say, be careful with the colour. Don't say that alkali metals are white. It's the compounds that are white, against the transition metal compounds that are coloured. It's not just the transition metals. So then, these are answers which you could give for the chemical properties. D then, the name given to group 0. That's a fairly straightforward question. The answer is noble gases. Part 2 then, what is the colour of neon? It's colourless. That's true for all noble gases. And part 3, why are group 0 elements unreactive? That's because they have a full outer shell of electrons. Don't just say a full outer shell. And this makes them stable. Question 3. Complete the table below. This is about indicators and the colour of phenolphthalein in acid. Well, it's colourless, and remember it's pink in alkali, and methyl orange is red in acid, and it goes yellow in alkali. B part 1. Balance summary equation for the reaction between magnesium and nitric acid. Well, magnesium is Mg, nitric acid is HNO3. You need to remember the formula of the acids: nitric acid, sulfuric acid, which is H2SO4, and hydrochloric, which is HCl. And when you've got a metal and an acid, it gives a salt. So in this case, it'll be magnesium nitrate. And hydrogen, which you write as H2. It's a diatomic gas. We need to balance it because we've got 2 nitrates here, so we need 2 nitrates over on the left. Part 2, 2 other observations during the reaction. Now it says other observations, so let's look to see what has already been given. We're told that it releases heat energy, so we can't say anything about heat increasing. Well, because there's a gas given off, there will be fizzing, or you can say bubbles or a gas given off. Don't just say hydrogen given of. The other thing is that the magnesium will disappear. A third thing that would be observed is that the solution is colourless. The solution that's formed is colourless. This magnesium nitrate solution, remember, compounds of groups 1 and 2 when in solution are colourless. And put in that it's formed because it's colourless at the start as well, so we want to emphasise that it stays or remains colourless. So any two of those three will be fine. C. Ammonium nitrate is an important fertiliser which can be produced from the reaction of nitric acid and ammonium carbonate. One other substance, as part 1, name one other substance which would react with nitric acid to form ammonium nitrate. Well, you could just simply use ammonia. And remember, when ammonia reacts with an acid, you just get the salt. You don't get anything else formed. Ammonium nitrate is a white solid. It would also be a colourless solution, so you could say that as well, but we're not told here if it's in the solid state or in the liquid state. So white solid or colourless solution. Part 3 then, after a balanced symbol equation for this reaction, well, ammonium nitrate is NH4NO3, goes to give nitrogen diatomic, so it's N2. Oxygen is diatomic, O2, and then water is H2O. Has to be balanced, so we need a 2 in front of the ammonium nitrate to balance the nitrogens, etc. And then on the left that gives, for example, 8 hydrogens. We've only got 2 on the right, so a 4 is required over on the right in front of the H2O. D part 1 is just a definition that you need to learn. So what do you understand by the term salt? So it's formed, it's a compound formed when some or all of the hydrogen ions, and they are in an acid, and they are replaced by metal ions or ammonium ions. Okay, part 2 is another balanced symbol equation between nitric acid and sodium hydrogen carbonate. Okay, so we'll start with sodium hydrogen carbonate, which is NaHCO3, nitric acid is HNO3, and this will form the salt, which in this case is sodium nitrate. You get water formed, and then when carbonates react, or hydrogen carbonates react, you always get carbon dioxide gas. That's already balanced. There's a clue there. The 2 marks indicates that it is already balanced. 2 observations. Well, you've got carbon dioxide gas produced, so you will see fizzing. Again, you can say bubbles or gas produced, but not just carbon dioxide formed. And the other thing is that the solid, or the sodium hydrogen carbonate, will disappear. There's a third possibility. So again, we've got sodium nitrate, and this is a group 1 compound, which in solution is colourless. So you could say colourless solution formed. Part E, have to calculate the percentage of nitrogen by mass in TNT. So you've got to work out the total mass of the nitrogen. Now you can see here that there are 3 nitrogens. Now the RFM of nitrogen is 14, so it's going to be 14 times 3, that is 42, and then you divide that by the total mass of the C7H5N3O6. So when you add all of that up, it comes to 227, and we want this as a percentage. So that is 18.5%. Okay, question 4. And we have to determine the empirical formula of nicotine. So I'm just going to draw out a rough table which contains carbon, hydrogen and nitrogen. Now we don't have mass values here, but we've got percentage, and you just treat percentages like masses. So you imagine if you have 100 grams of it, or 100% of something, then that's going to be equivalent to mass. So we've got 74.6 0.17% or grams. So I'm just going to write mass here, that are carbon, then 8.61 hydrogen and 17.22 nitrogen. Now I've got to work out the number of moles of each of these. So I'm going to divide this by 12, and that works out to be 6.18. Here was 8.61 over 1, which is just 8.61. And then 7.22 divided by the RFM of nitrogen, which is 14. Now it's not N2. You don't do N2 and H2. It is just the mass of one single atom. So that works out to be 1.23. Now we want a whole number ratio, which is what empirical formula is. It's the simplest whole number ratio of atoms in a compound. So we're going to divide through by 1.23. So that will give us 1. So that then will go into 8.617 times, and then it'll go into the carbon, or go into 6.185 times. So the formula is C5H7N. Part 2 then, we have to determine the molecular formula. Now I'm just going to write down the empirical formula over to the right, so to remember what it is. Now the molecular mass, or the molecular formula, is the actual number of atoms in a molecule. And the total mass of this molecule of nicotine is 162. So what you've got to do is work out the mass of this, and that equals 81. So hopefully you can see that you need 2 of these to equal 162. So what we do is multiply all of these by 2. So that means that in total there would be 10 carbons, 14 hydrogens, and 2 nitrogens. We do not do 2 C5H7N. Part B then. So we have to look at this equation, and I've got 200 grams of sodium hydroxide. Just write it in underneath. We're added to 142 grams of chlorine. Okay, part 1, calculate the number of moles of sodium hydroxide. Well, moles equals the mass over the RFM, and sodium hydroxide, when you add that up, is 40. So that gives 5 moles. Next one, calculate the number of moles of chlorine. So again, it's going to be 142, the mass, divided by the RFM. Now chlorine, as you can see here, is Cl2. So that's going to be 35.5 times 2, which is 71. And that works out to be 2 moles. Part 3 then, we have to determine which reactant is limiting. So I've put the answers to the previous questions over on the right. I'm going to answer it in here, which I will remove afterwards. So I'm going to put in the reactants, and we've got 5 moles of the sodium hydroxide to 2 moles. So what you can do is work out a 1-to-1 ratio. So we're going to divide the 5 by the 2, and that would work out to be 2.5. Now the chlorine already is in a 1 ratio. There's a 1 here, so it would be 2. And then we can see which one is the smallest number, which is obviously the 2. So that means that chlorine is the limiting reactant. Or what you could have done is just look at this. This is 2. Chlorine reacts with sodium hydroxide in a 1-to-2 ratio. So if there are 2 moles of chlorine, that means there would have to be 4 moles of sodium hydroxide, or at least 4 moles of sodium hydroxide. Well, we've got more than 4. So I'll just put that in. We're going to multiply that by 2. There's 4. And you can see, obviously, that we've got more than 4. So that means the sodium hydroxide is in excess. Therefore, the chlorine has to be limiting. Now, you could do it the other way. If you start off with 5 moles of sodium hydroxide, how many moles of chlorine are required, or the minimum moles of chlorine that are required. Well, because it's 2 to 1, we would divide the 5 by 2, and that would produce 2.5. So that's the minimum moles required. Well, you can see that we don't have that. We've only 2. Therefore, the chlorine is limiting. Okay, then on to part 4. Calculate the mass of sodium hypochlorite. Okay, and I'm just going to write part of the equation in. So we want to work out this, and we've determined that the chlorine is limiting. So over here, we're going to use 2 moles of chlorine. It's a 1 to 1 ratio. So that means that the moles of sodium hypochlorite formed will be 2. Remember, we don't use the moles of sodium hydroxide because that's an excess. It's the limiting reactant which determines the total mass of product that can form. So now we know the moles of sodium hydroxide, we can convert that to a mass. There's going to be 2 times the RFM, which is 74.5, and that works out to be 149 grams. Question 5. Solution of potassium iodide was prepared by weighing out 39 grams of the iodide and adding it to 25 grams of water. The boiling tube was placed in a beaker of water. Okay, so I'm just going to make a note of this. So the boiling tube was placed in a beaker of water and was heated using a Bunsen burner. The contents were stirred using a thermometer. So there's got to be a thermometer inside this boiling tube. Now for part 1, we have to draw a diagram of this. Okay, if we start off with this first bit, boiling tube was placed in a beaker of water. Okay, so there's my boiling tube. And I'm going to draw the beaker. It doesn't have to be a work of art. So there's my beaker, and there's water in the beaker because it's placed in a beaker of water. And then the next bit is it was heated using a Bunsen burner. So this must be sitting on a wire gauze and tripod. We don't need to draw the Bunsen, just write the word heat with an arrow. And then the last thing is that the boiling tube contents were stirred with a thermometer. So I need a thermometer in here. Okay, it doesn't have to be too fancy. Now, still not finished. A couple of things I need to do. Because this bit here tells me that potassium iodide, or solution of potassium iodide, was prepared by weighing out 39 grams of the iodide and adding it to 25 grams of water in a boiling tube. So this boiling tube then contains the solution of potassium iodide. And we're told the diagram has to be labelled. So all of that's needed for 3 marks. Part 2 is just a definition of the term saturated solution. And part 3, I have to calculate the solubility of potassium iodide at 35 degrees Celsius. So I've brought in, from the start of the question, information that we need. We can see that 39 grams of the iodide were dissolved in 25 grams of water. And the units of solubility are grams per 100 grams. Well, to go from 25 to 100, multiply by 4. Therefore, this must be multiplied by 4. So it's going to be 39 times 4, and that works out to be 156 grams per 100 grams of water. Okay, on to B. Yes, this is question B. Again, I've just moved the graph so it's alongside the questions. So part 1, what's the solubility of potassium iodide at 70 degrees C? Okay, we just go to 70 degrees C and you read off from the graph. And that works out to be 184. Now that's the only thing it can be because it's clear there that it is 184. Number 2, or part 2. A hot solution of potassium iodide contains 192 grams and it's in 100 grams of water, okay, which is what the graph is. And it's cooled from 90 to 30 degrees C. Okay, so let's look at 90 degrees C. Now it can hold up to 200 grams. So we're going to start off, so this solution is not saturated. So we're going to then start cooling this down and then determine when the crystals will start to appear. So you've got to work out the temperature at which the solution is saturated when 192 grams are present. So if we go up to 192 and across, we see that that equals 80. So if you have this solution and it's at 90 degrees with 192 grams in it, so let's say it's here, and we start cooling it, the crystals will form at 80 degrees C. Part 3. A saturated solution of the iodide in 250 grams of water at 60 degrees was cooled from 60 to 30. What mass of crystals was deposited? Now remember, the solubility curves are always per 100 grams of water, so you've got to work that out first. So work out the mass that's required to saturate it at 60 degrees C and 30 degrees C. This is a saturated solution, so you have to work out the solubility values at 60 and 30 degrees C. So we'll do 60 degrees C first. So go to the graph, read it off, and you can see that's 176 grams. That's per 100 grams of water. So do the same sort of thing for 30 degrees C. Go to the graph, read across, that's 152. So if there were 100 grams of water cooled from 60 to 30 degrees C, the mass of crystals deposited would be the difference. That would be 24 grams. Now the question is asking us for the mass deposited in 250. So 24 grams in 100 grams of water. Well, to change the 100 grams to 250, we would divide by 100 multiplied by 250. So we're going to divide by 100 multiplied by 250. And that gives an answer of 60 grams. Final question, or final part of the question. Test for ions. See part 1. Based on the results above, write the formula of the anion and the cation present in X, Y, and Z. Okay, so let's start with X. We've got sodium hydroxide being added, and we get a green precipitate. Okay, so that tells us right away that it contains iron 2. With barium chloride solution, there's a white precipitate. Well, barium chloride solution tests for sulfates. If there's a white precipitate, it means there's a sulfate. So X must contain iron 2 because of the green precipitate, and then sulfate. If it had been iron 3, then this test would have produced a brown precipitate. Okay, on to solution Y. Flame test, yellow flame, so that tells us contains sodium ions. So I'll just put in sodium ions here, and then no reaction here, none here. Okay, so it's not a sulfate, but there is a yellow precipitate with silver nitrate solution. So when you see silver nitrate solution, you should automatically be thinking of chloride, bromide, or iodide. And when we get a yellow precipitate, that means it's an iodide. So solution Y is sodium iodide. On to the last one. Okay, no flame test. Brown precipitate, okay, well I mentioned that over here. That contains iron 3 this time. And no reaction here, so it doesn't contain a sulfate. But there's a cream precipitate with silver nitrate solution. So again, it's a halide. It's obviously not iodide. This time it's cream, so it's bromide. Chloride would produce a white precipitate. And then part 2, name the white precipitate formed when barium chloride solution was added to solution X. That's this one here. Well, the barium ions in barium chloride solution react with the sulfate ions and they form that precipitate. That's a solid that forms when 2 solutions are mixed. So it's barium sulfate. And it's asked for the name, so you don't write BaSO4. The ionic equation for that, now you're not asked for it, I'm just going to put it in, would be as follows. You have the barium ions from barium chloride solution would react with the sulfate ions in solution, and then that forms your insoluble solid of barium sulfate. But the name is the only thing that's required here.